So welcome back. In our previous video, we talked about the function de base, and we said the recursive function is a function that can be constructed from two parts. We had a tree where we said the function de base, the base functions, and the constructive rule, that's the règle de construction. So the last video we talked about the function de base, and now we're talking about the règle de construction. For règle de construction is divided into two parts. It's divided into the règle de composition and the règle de recursion. For the règle de composition, it's the whole idea, like in algebra, when we talked about in algebra we have the f rangé, the h rangé, where I should write that down, let's say I have f rangé is the same thing as me saying f of g of x. If I have h rangé, is the same thing as me saying h of g of x. So that's how the regular composition is. You compose functions, you see. So you compose functions. So we'll talk about the regular composition, and after that we'll talk about the règle de recursion. For the règle de composition, let's say we are giving function g. So soit or given g1, g2, g3 up to gk. So we're having g1, g2, g3 up to gk. This is we're having k functions. The definition is that soit g1, g2, g3 up to gk, k fonction d'arité n. I'll explain. A h une fonction d'arité k. I'll stop here so I can break it down. Soit G1, G2, G3 jusqu'à GK, K fonction d'arité n, et H une fonction d'arité K. The first part, G1, G2, G3 jusqu'à GK, K fonction d'arité n. Why it's like that is because if, like, I should get right on a new paper. Let's do that here so we can see. Let's do that here. So basically, if we have this, why is it d'arité n? Why are we saying k function? I mean, so that's what we're going to break down here. It's basically G1 is a function, G2 is a function, G3 is a function, G4, G5 jusqu'à GK, like GK, jusqu'à GK. So we have like G1, G2 up to GK. So that's why we say K function. Okay, so d'arité n. Why is it d'arité n? So G1, we said it's d'arité n. So that basically means we're having this, just like we tweeted the last time, G1 jusqu'à Gn. I mean, because a function, this is a remark, a function is like, apart from when it is a constant, it is always associated with a variable or more variables. So that's why it is d'arité n, because we can have n variables associated with the function G1. It goes down to GK, same n puissance n, because like I said, it is associated with one or more variables. So that's why we're having car fonction d'arrêté n, which is a general definition, okay? For règle de composition, which is what we're treating now, I should make it the heading. Looking at règle de composition. So, for the règle de composition, its definition is giving G and G2 up to Gk car fonction d'arrêté n, and H is a function d'arrêté car. Now, we'll all be like, so how is H a function d'arrêté car? I'll break it down. H is a function d'arrêté car because now we've already started composing. We're having two functions. If we have two functions in the same place, we have the opportunity to compose, because here we're dealing with the règle de composition. It means hash rangé, just like we said the last time. So if we have hash rangé, we know it's the same thing as h rang g1, like we did here. So h rangé de x, you see. But in this case, we're having car fonction g1, g2 jusqu'à gk, car function, and we have one or more variables. We don't know how many variables, so we're trying to make a general definition of it. So this is g1, h de g1, g2, g3 jusqu'à gk. That's why we say h is a function d'arrêté k, but g is a function d'arrêté n, and h is a function d'arrêté k. I hope it's clear. Yeah, so that's why we have h is a function d'arrêté k and g to gk car function d'arrêté n. Now, here again, another thing we have to put into consideration is that's now where the main definition is coming from. We've spoken about G, we've spoken about H, now it's F. F is the composite of this function, of these two functions, H and G. It's like, I'll bring this back, let's see. So this is hash rangé, H rang G. I will note this as F. I'll say this is equal to F. So this is the composite of the function. F is H rangé. I make F the surrogate of the formula. So that means F is equal to H rang G1, G2, G3 up to Gk. And F est une fonction d'arrêté n. Now you're like, what's all this? We've not finished absorbing the other one, and now you're telling me that F is d'arrêté n. Okay, how is F d'arrêté n? I'll tell you. F is a function d'arrêté n because just like we did here, I'll bring back this paper. We have h rangé is h of g of x. So remember, this is F. H of g of x. We can have one or more variables. So this hash rangé, breaking it down, is the same thing as h of g1 de x1 jusqu'à xn, g2 de x1 jusqu'à xn, g3 de x1 jusqu'à xn, up to gk jusqu'à x, de x1 jusqu'à xn. You get it, right? So now I can say this is h en g1, g2, g3 jusqu'à gk de x1 jusqu'à xn, because the x1 jusqu'à xn will keep multiplying with the g1, g2 and g3, and then we'll get this expression again. So at the end of the day, it means we are going to have this f de n puissance n vers n de x1 jusqu'à xn, and it's going to be associated with this function that we have just right above. Now this, remember, this whole thing is f. So this is f and this is f. Remember, f. So it's almost like us just having f of xn, this guy xn, which is derivative n, which we've been seeing in our previous examples. And so that's why it's derivative n, because we're posing h on j to be f, and so it's f from the x jusqu'à xn, and so that's why it's derivative n. So in summary, f is a function derivative n, and it's said to be constructed by composition from h and g1, g2 jusqu'à gk, and we define it as this. Okay, so that's règle de composition. So at the end of the day, we know that g1, g2, g3 jusqu'à gk, k fonction derivative n, h is derivative k, and f is derivative n for règle de composition. Now, cas particulier. The cas particulier brings us back to the h rangé. So, for the cas particulier, let's assume k is equal to 1. That's the cas particulier. K is equal to 1. If k is equal to 1, let me bring this up a bit. If k is equal to 1, what does that mean? If k is equal to 1, just write it here. We know f is derivative n, h is derivative k, and g is derivative n. So if k is equal to 1, that is this k, if it's just equal to 1, that is we're having just, so we're having f is equal to, if k is equal to 1, it means we'll have f is equal to h rond g, right? So if k is equal to 1, we're having h rond g. Take this out. Okay, just write it here. F is equal to h rond g. So what does that mean? What's the arity of the functions? If k is equal to 1, g is still derivative n, because if it's still g1, is g1 associated with what? N variables. So g remains derivative n. H, how about h? We said h is derivative k, and here k is equal to 1, and so h is derivative f. F is still derivative n, because if we take this to be this, like we said, we pose this to be f, is f rond x1 jusqu'à xn, so f remains derivative n. And so at the end of the day, we're having f is equal to h rond g, which is equal to h de g de x1 jusqu'à xn, and c'est une fonction derivative n. Oh, you can see that. Yeah, it's une fonction derivative n. So that's for règle de composition. Now we'll look at règle de recursion. Recursion. I still go for French classes. The only difference is that I study in French, so whichever way, the understanding is what's important. So the règle de recursion, okay, it just like we've discussed for the règle de composition, it also has its definition for règle de recursion. For règle de recursion, we are giving 3 functions as well. We are giving g, we are giving h, we are giving f. And let's say given so let's say given g in function dérivée n, I think now we know why it's dérivée n, because of the g de x1 jusqu'à xn. So g est une fonction dérivée n et h is a function. In this case it's not k, okay, in this case it's a function dérivée n plus 2. h une fonction dérivée n plus 2. That means f would be a function dérivée n plus 1. f is a function dérivée n plus 1. So that means f is the recursivity of g and h. That's how we get the n plus 1, recursivity of g and h. That's f. Okay, let me break it down. So it's defined par recursion à partir de g and h comes with, let's say, let me break this down. Let's assume, I should use the pink one. Let's assume that f is dérivée n, not n plus 1 now. Let's assume it's dérivée n. And we know that f is the recursivity of g and h. Now we're assuming f is dérivée n. So if f is dérivée n, what does that say about g and h? You notice here that if f is dérivée n plus 1, h will dérivée n plus 2. That means 1 was added and we got n plus 2, which is the derivative of h. And here it is n, meaning it was like we subtracted 1 from our function f and then we got n, which is derivative of g. Exactly the same principle here. If f is dérivée n, it means to get g we subtract it with 1, to get h we add 1 to our n and we get for h. So h will be a fonction dérivée n plus 1 and g will be a fonction dérivée n moins 1. That's recursivity. Like, it's a recursive function. It's a recursive function. And so generally we define the règle de recursion comes with, I should do it on a new sheet. So generally we define the règle de recursion comme ça: f of x1 jusqu'à xn, I'll use another pen here, 0 give us g de x1 jusqu'à xn. You should advise you put this in your record book, like I said, because we'll be using it when we start actually solving exercises on Calculabilite. And this is the first part. When you're doing for règle de recursion, you have to first pass through the first stage, and then the second stage, I was supposed to use a red pen here. Okay, just try. And the second stage is f de x1 jusqu'à xn and y plus 1 to give us h x1 jusqu'à xn, f of x1 jusqu'à xn, y and then y. I'll give us two examples which are Calculabilite, and maybe from there we'll be able to look at the concept of what this definition is actually talking about. So we'll look at the Calculabilite. Calculabilite we'll look at for when n is equal to 1 and for when n is equal to 0. So if n is equal to 1, it means we're having f of x1, which we can also say f of x. So we have f of x 0, f of x 0 will give us g of just x because n is 1. That's the first stage. For the second stage, it will be f of, remember, x is 1, n is 1, so just having x and then y plus 1, which will give us, oh, don't have a lot of space, let's see, which will give us h of x, then f of x, since n is equal to 1, it will be f of x comma y and y. Now, if n is equal to 0, same thing. The only thing here is n is equal to 0, but normally we start from 1. And so we don't have x, but we have 0. So our 0 remains. And so we're just going to have g of 0. So we have no variable. I remember when we said we don't have any variable, we take it as a constant. And so this becomes constant. The second, this is because we have g of 0 and g of 0 get a constant because we don't have variables present. The second, same thing, we don't have variables, so we have just y plus 1. And so we're having h, we don't have variables. And so we don't have variables, and we have just f of y and y. And remember when we said constant functions, their derivative 0. So that's what we have for règle de recursion and what we have for règle de composition, under règle de construction, and then we talked about the base functions. So in our next video, we are going to still be talking about calculability because it's kind of a broad topic, and we'll try one simple example on règle de composition, and we'll look at primitive recursive functions and how we can use function de base and règle de composition to solve primitive recursive functions. So thank you for watching, and see you in the next video.